So, hello everyone, Radhe Radhe, and welcome back to my channel. Today, we're continuing the Road to Expert series. Today, we have our episode 4, and today, we're going to discuss two CSES problems as well. Okay, first of all, I would like to apologize because I wasn't uploading for 2 days. It was because I was working on a freelancing project, and that mostly took most of the time. So, uh, I'm sorry. But, anyways, coming back to today's topic, let's get back to the video. The first problem is distinct value subsequences. So first of all, I would advise you to pause this video and give this problem a try. It's not that difficult. Um, some combinatorics and some math is involved to solve this problem. But anyways, if you have tried, then let's begin. Let's discuss this problem. So given an array of n integers, count the number of subsequences where each element is distinct. A subsequence is a sequence of array elements from right to left that may have gaps. Okay. So we need to print the number of subsequences with distinct elements. The answer can be large, so print it modulo 29 plus 7. Okay. So the problem itself is very simple. So we have been given an array, right? And we can pick a subsequence such that each element in the subsequence has to be distinct. So if I pick a 1, 2, 3, this is a valid subsequence. If I pick a 2 and 3, this is a valid subsequence. A 2 and a 1 maybe, right? A 1 maybe, right? So these are, I'm saying that these are the valid sequences, okay? And we need to print the total number of these valid sequences, right? If you will see a invalid sequence or invalid subsequence would look as 1, 2, 3 and a 1. So you'll see that 2 is unique, 3 is unique, but 1 is not a unique, or 1 is not distinct, right? 1 is occurring twice in this array or in this subsequence, I'm sorry. So if 1 is occurring twice, then this condition fails, right? That each element is distinct. So we cannot take this subsequence. We cannot take a 1 and a 1, right? A 1, 2 and a 1, a 1, 1, 3. We cannot take these type of subsequences, right? Okay. So we need to calculate the total number of subsequences or total number of valid subsequences. So how do we visualize this problem? So first of all, if I write each element and map it to its frequency, so let's say if I have 3 and it occurs 2 times. If I have a 4, it only occurs once, so it occurs 1 time. If I have a 5, which occurs 3 times, and then I have a, let's say 6, which occur only once, so 1 time. And so this is our array, okay? We have 3 2 times, we have 5 3 times, we have 4 ones, and we have 6 ones. So you can imagine an array like 3 3, 5 5 5, 4 and a 6. So maybe let's consider this as an array for now. So I'm saying that first of all, I can only choose 3 ones, I can only choose 5 ones, I can only choose 4 ones, or I could only choose 6 ones, right? So we basically have, okay, let's put it this way, that if I need to form a valid subsequence, an element cannot occur more than once. So whatever is its frequency, so let's say if an element ai occurs x times, so whatever may be the frequency, I need to choose a single element from that. So wouldn't that be x choose 1, right? Because I need in forming the valid subsequence, I need to just pick a single element from all of its occurrences, right? So if let's say AI occurs 10 times, then I can only choose that AI once, or I can not choose at all, right? So let's say if I have this 3 which occurs 2 times, so either in forming a valid subsequence, either I could choose this 3, or I could choose this 3, or I do not choose any 3 at all. So we have 3 choices for this 3, right? So when you remove the not choosing one, that is we can either choose this 3, or we can either choose this 3, right? So this becomes 2c1, right? Out of 2 elements we can choose any one, so this is xc1. If AI occurs x times, this is xc1. So if we expand this is nothing but x factorial upon x minus 1 factorial into 1 factorial, which again becomes x into x minus 1 factorial upon x minus 1 factorial. 1 factorial is just 1, right? So we can cancel this term, and this is just equal to x. So x choose 1 is nothing but x only. So now it would be much more intuitive that for 3 we have nothing but 2 choices. This is x was the choices, right? Or the number of occurrences of that particular element. So if 3 occur 2 times, then we have 2 choices to pick 3. We can either choose this 3, we can either choose this 3, right? Or else what we can do, we cannot pick any 3 at all. So instead of choosing this 3 or this 3, we decide not to take any 3 at all, right? And similarly we do that for all the cases and multiply all the results. So let's say for 5 also we have 3 choices, so we can either choose this 5 or this 5 or this 5, and out of all the 3, I mean 5 is occurring 3 times, right? So we have 5 C1 choices, which boils down to, or I'm sorry, 3 choose 1 choices, or 3 C1 choices. So that boils down to nothing but 3 itself, right? So we have 3 choices to 3 options for this 5. But if you'll see, we also have one option where we choose not to include any 5. So we have 4 choices for picking this 5. So we have 4 options for picking this 5, and we have 3 options for picking this 3 options. Again, for this thing, the element which are occurring only once. So let's say I have a 10 also here. I'll add that to my map here also. So these elements occur only once, right? So if they occur only once, then what I can do, we can either choose this element or not choose this element, right? So we have 2 choices for this one. Similarly, we can either choose this 6 or we cannot choose this 6 here. So this boils down to 2 choices. Similarly, this also boils down to 2 choices. So now we can just multiply all the result, right? We have these 3 choices, so 3 into, we have 4 choices for 5, so into 4 into, we have 2 choices to choose this 4, we have 2 choices to pick this 6, we have 2 choices to pick this 10 also. So this is 2 to the power 3, and we will subtract a 1 from this answer. Why? Because if we do not choose any element from this, if we do not choose any element from this, not from this, not from this, not from this, so this is an invalid choice, right? So we'll subtract 1 from it to counter the case where we do not pick any element in the subsequence, right? So we have to include that option also, and so that would be it. This is our final answer. So this is nothing but length plus 1, or this is just frequency plus 1 into, this is frequency plus 1 into the number of elements which occurs once, the length of that, 2 to the power or 2 raised to the length of this element which occurs only once, right? So 3 elements occur only once, so we have 2 choices, right? Or we can keep on doing this also, that we take a 3, we take a 4, and then we can keep multiplying this. We can do nothing but increase the frequency of these elements by 1. So I increment this 2 by 1 because we other than picking a 3 from here and here, we also have an option to not pick 3 at all, right? So we have 3 options in total to pick this 3. Similarly, for picking this 5, we have 4 options. One for these 3 and one for when we do not choose to include any 5. Similarly, for this 4 also we have 2 choices, either pick this or not pick this, so 2. For this also we have 2 choices, so 2. For this also we have 2 choices, so 2 and a -1 to counter the case where we do not include any element at all. And this will give me a final answer. So this is 8 for the 32 and 32 6 and 96 it is, I think. This would be 95. 2 to the 4, 4 to the 8, 8 for the 32, and then this is 6. Yeah, this is 96. So this is 95. This would be my final answer. And these will be the total number of valid subsequences. So if I just repeat the part, so we cannot in a valid subsequence we cannot choose a single element more than once, right? So we can only choose an element once per subsequence. So that gives us extra that leaves us with, if we have x elements of same frequency, or if we have x same elements, then we can only choose one of them. So that gives us with xc1, and we'll also include one choice for the case where we choose not to include that element, and we'll do that for all the elements, right? And that would be it. We'll just multiply all the result, and that would give us the final answer. That's it. You can take the modulo as well. By performing the multiplication operation, you can also take the modulo, and that would give you the right answer, right? And that's it. So this is the code for the problem. I'm actually using binary exponentiation to do a to b. I'm sorry, I didn't do like take all the frequency and then multiply that by frequency. So what I'm doing in this code, I'll just show you guys the code. So I'm taking the frequency first of all, and then if my frequency is just 1, then I'll increment by length, because the element with frequency 1 will only have 2 choices, right? So I'll at the end raise my 2 to the power to the frequency of element, right? And if the frequency is more than 1, then I'll do a p plus the frequency plus 1, and I'll multiply that with the answer. The plus 1, as I said, is for the case where we choose not to include that element, right? And then we can raise 2 to the power the length of the element which had frequency 1. We can take the modulo after performing the operations continuously, and then we'll subtract 1 from it to counter the case where we choose not to include any elements, right? So we do not pick any element from this set, from this set, from this set, from all the sets, right? So that would be one case, and then we'll just subtract that case and take the modulo again, and this will give us the final answer. That's it. So I hope you got this problem. This wasn't very difficult, to be honest. Let's move on to the next one. 2 sets. So the problem says your task is to divide the numbers from 1 to n into 2 sets of equal sum. The only input line contains an integer n. So we have been given n natural number, n starting natural numbers, right? And we have to divide that n natural number into 2 equal sets, right? Such that their sums must be equal. So I should print a yes if the division is possible and no otherwise. After this, if the division is possible, we should print an example on how to create such the sets. First print the number of elements in the first set followed by the number. Okay, so we do not only need to find if that is possible or not. If that is possible, then we need to print both the sets, right? So how will we do this? So the first observation is that it would become a standard dynamic programming problem if we didn't have those first n natural number, if we had something like, if the question would have said that we have some element from array A, so array A would have been like something like a1, a2, a3 up to n, and then you need to divide these elements into two non-empty sets such that their sums must be equal. So in that case we would have used a dynamic programming solution, because this is a standard dynamic programming problem. But since in the problem they said the numbers are from 1 to n itself, right, always, and we now need to divide those numbers into two equal set. So what this problem is saying, that if we have a 1 2 3 4 5, let's say 6, so if our n equals to 6, we have these elements, and we now need to divide these elements into two sets such that their sum must be equal. So I'm saying the first observation that comes to my mind is that if the total sum of n natural number is odd, then we can never do that. The total sum, we denote that by n into n plus 1 by 2, right? This is the sum of n natural number from 1 to n, right? So if my n is 6, then I could do a 6 into 7 by 2. So this is 21. So that means that no matter what I do, I would never be able to create two sets such that their sums would be equal, because this is an odd element, right? And if you add two elements, let's say to get an odd, we'll have to do something like even plus odd, that would give us odd, or odd plus even, that would give us odd. Otherwise, if you add an even with an even or an odd with an odd, that would give us even only. So we can conclude that the frequency or the total sum of both the sets will be different, because one is even and one is odd, right? And even and odd both cannot be same at the same time. So that leaves us that if my n into n plus 1 by 2 is odd, then we can never partition this set, so we'll just directly print a no from here. Otherwise, if we would have had something like n equals to 5, so let's say 5 into 6 by 2, this is 15, this is also not possible. Let me take something else. N equals to 7, 7 is 7 into 8 by 2, this is 28. Okay, so for n equals to 7, the total sum comes down to the total sum comes down to 28. So that means the total sum of the elements or n natural numbers are now even. So we know that even can be divided into two equal parts, right? 28 could be divided as a 14 and a 14, right? So I'm saying that if my total sum of the n natural numbers, or if my n into n plus 1 by 2 is even, then my answer is always possible. And if it is odd, then my answer is always not possible. We'll just prove that now, how we're coming to this conclusion that if it is even, then it is always possible. So we'll just come down to that. But if you will see carefully, for n equals to 7, the sum is 28, right? So let's try to divide both the sets into sum of 14. So first set will also contain 14, and another set will also contain 14, and that is the only possible solution, right? For both sets to have equal sum, both should have n by 2 and n by 2, right? Or sum by 2 and sum by 2. The set 1 will also have total sum as sum by 2, and set 2 will also have a total sum of sum by 2, right? Because if you add them both, this is sum by 2 plus sum by 2 will actually become 2 sum by 2, which eventually would give us sum. So the total sum is actually maintained, nothing is lost. So this is only a valid construction. If my sum is 28, then we can only give a 14 to the first set, and we can only give a 14 to the another set, right? So now let's try to make both the sets. Let's try to construct both the sets first of all. So I'll for now have my total is 0. I'm just maintaining a total for now, right? So I'm saying I'm iterating from the last element. Okay, I'm currently creating the first set. So is total plus 7 or total plus the current element lesser than this sum by 2? Just equals to k. I'll just assign this by k. This k is sum by 2. So k is equals to 14 here, right? So is my total plus 7 is less than equals to 14? Yes, sure, it is less than equals to 14. So I'll take this element and I'll add this to my total. So now my total becomes 7, and I'll move on to the next one. So now my total plus the current element is less than 6 or less than equals to k. Yes, sure, it is less than equals to 14, because 7 plus 6 is 13, which is lesser than equals to 14. So I'll add a 6 here. So this will leave me with 13, and I'll move on to the next one. Now is my total plus the current element, which is 13 plus 5, is lesser than equals to 14. So 13 plus 5 is 18, which is greater than k, right? So this will not satisfy the condition. Now we will move on to 4. So is 13 plus 4 less than equals to 14? No. So we'll keep on moving until we encounter 1. Now is 13 plus 1 lesser than equals to 14? Yes, sure it is. So we'll assign this, we'll make this total equals to 14, and we'll use this element. We'll use this, not this one, this one and this one. And I'll add all these elements, all these used elements to my first set. This is nothing but 1, 6, 7, and the rest of the elements would be assigned in the set 2, 2, 3 and 5, 2, 3, 4, 5, I'm sorry. And now you can see that both of the set will have sum equals to 14. Just 7 plus 6 is 13, plus 1 is 14. 5 plus 4 is 9, 9 plus 3 is 12, 12 plus 2 is 14. So this is also 14 and this is also 14, and this will always work. Now let me prove why this will work in just a minute. But I hope you guys got the point that if my total sum of n natural number n into n plus 1 by 2 is odd, then we can never do it. So we'll directly print a no. Otherwise we can always do it. How we will always do it, I'll just come to that. But if my total sum is, let's say, even, or so then in both of the sets I could have an sum by 2 and a sum by 2, right, for both of them to be equal. Because I need to divide all the elements. So if say I have some elements from 1 to n, so I need to divide all. I could either pick this one and move into the set 1, or I could either take this one and move into set 2, right? There's no option of not including that element, right? We cannot just skip this element. We either need to place this in a S1 or the set 1, or we either need to place it in the set 2, right? So we cannot skip this. So if we cannot skip this, then what we are left is both the set should have equal sum, and we cannot skip any element. So then the total sum of both the elements must be sum by 2, right? Otherwise it is never possible. I'll advise you to think it through, try to digest this on your own, try to come up with more cases to counter this, but you'll see that sum by 2 is the only possible construction. So when you had digested this solution, that sum by 2 is only a possible sum for both the sets, then we can try to move on and prove that why sum by 2 can always be made. from the current set of n natural numbers. So for that you'll have to prove this with prove this with or let me try to put it this way, that okay, so we need to prove that we can always make k, or k is equal to sum by 2. So we can always make k. So if we can always make k, this is nothing but sum by 2. So my total sum was sum, and if I can always, let's assume for now that we can always make this k. So if I can always make this sum by 2, then sum minus sum by 2 is nothing but sum by 2. So I can also make another sum by 2. So my both the subsets are now balanced, right? This is saying that my both the subsets are now balanced. Now we only need to prove that I can always make k, or I can always make sum by 2. To prove this, I'll prove this by contradiction, that if I had some number, let's say I have numbers from 1 to 5, then I'm saying that I can make all the numbers from n plus 1 to n into n plus 1 by 2 by using these numbers. So I have 5 numbers, so I'm saying that from 6 till 5 into 6 by 2 is what, 15, right? So from 6 to 15 I can make all the numbers by using these numbers. How? So let's consider. So for making a 6, I could just take a 5 and add 1 to it, so I can make a 6 obviously. To make a 7, I could take this 5, add a 2, so I could make a 7. For 8, 5 and 3, I could make a 8. For 9, 5 and 4, so this is 9. 10, I could take a 5, a 4, 9 and a 10, so this is 10. 11, I could take a 5, a 4, 9 plus 2, 11, so I can make a 11 as well. 5, 1, 4, 9, if you add a 3, this is 12, so I could make a 12. 5, 4, 9 is 5, 4 is 9, 9 plus 3 is 12, 12 plus 1 is 13, so I can make a 13. 5, 4 is 9, 9 plus 3 is 12, 12 plus 2 is 14, so I make a 14. Now 5 plus 4 is 9, 9 plus 3 is 12, 12 plus 2 is 14, 14 plus 1 is 15, so I could make a 15. So I saw that by using only these 5 numbers, I made all the numbers from n plus 1 to n into n plus 1 by 2. Right? So I can make all the numbers by using these n natural numbers, or first n natural numbers. I could generate all the numbers from n plus 1 to n into n plus 1 by 2. So sum is what? N into n plus 1 by 2. N into n plus 1 by 2. And sum by 2 is what? N into n plus 1 by n into n plus 1 by 2 by 2. So this boils down to n into n plus 1 by 4. So if I can make all the elements from n plus 1 into n plus 1 by 2, then I can also make this n into n plus 1 by 4, right? Why not? What's stopping me from making this n into n plus 1 by 4? This is the total range, then we can make elements, right? To prove this, why we can always make these numbers, you'll have to do this mathematically. I think there was a proof on stack exchange, something like that, that we can always form such elements by using the first n elements. There was some proof, I read it some time back. You can read it if you are interested, but for now I'm saying we can make all the numbers from n plus 1 by using natural numbers, or first n natural numbers from 1 to n. I could make all the numbers from n plus 1 into n into n plus 1 by 2, and if I can make all the numbers from n plus 1 into n plus 1 all the way up to n into n plus 1 by 2, then I can also make this number, right? N into n plus 1 by 4. What's stopping me from making this number if I can make all the numbers from this? This must be somewhere in between only, right? So that way I can conclude I can always make this number, and then I will try to make this number. by iterating from the last element itself, right? Why we are iterating from the last element itself? You need to prove this greedily that we can always form such a number if we move from the last to the first. You can always do that. For that, you'll actually need to consider cases and prove this by yourself. This I cannot explain everything in this video, so you'll have to prove that, or you can Google it and try to prove this. But we'll iterate from the last element, and we'll maintain a current sum. If my total sum plus the element I'm on is lesser than equals to the k, then I will pick this element, add that to my first set, and then move on to the next one, increment my this sum variable. If I was maintaining a sum, then I will increment this. If it was initially 0, I will increment this by the current element. I'll move on to the next one, and I'll add this to my set. So after all the iterations, all the elements, let's say these elements were marked as used, and so all the elements which are remaining from the set, they will go to the set 2, and all the elements which have been used will remain in set 1. So that way we'll obtain a valid construction for both the sets, and then we can just print the length and the elements of set 1 and then set 2, and that's it. I hope you got it. This was a little trickier if you didn't knew this trick, that we by using n natural numbers we can make all the numbers from n plus 1 to n into n plus 1 by 2. This is a very important, I think, observation, that this comes handy in a lot of problems, especially in some tree problems on Codeforces. So anyways, I hope you got it. Take your time to digest this problem. I'll show you guys the code in the meantime. So this is the code. So my target is equal to sum by 2, which is my k. If my target eventually becomes 0, I can just break out of the loop. If my target is greater than equals to I, then I'll just decrement, or I'm not maintaining a sum here, I'm just decrementing the target itself. So I'll just decrement that I from the target. I'll mark the current element as visited, and I'll maintain a count also. So I'll first check if my sum is odd. If my sum is odd, I could directly return a no. Otherwise, I can print a yes. I could print the element, the count of the first set. I could print the element of the first set because we marked them as visited. Now we can print the remaining elements, which is the elements of the set 2. The n minus count will be the count of elements of set 2, and the elements which are not visited from 1 to n, those will be remaining in the set 2. So I'll just print them, and then that's it. This is the total code, and this is it. So I hope you got the problem. I hope you enjoyed it. We'll continue the Road to Expert series again, maybe tomorrow, and I hope you enjoyed the problems. Give them a try to do everything, take your time, do everything slowly. Try to understand every piece of information, every piece of thing that you use, and then I'll see you guys in the next one. Bye bye, thank you, and Radhe Radhe.